back. It's good to see everyone here today. Just going to continue down the same path. I recognize that this topic is a little dry. Let's just get through it, and maybe we'll all learn a little bit along the way, and then we'll really be diving into graphics rendering starting on next week. One other just point of order. I mentioned this on Tuesday. I'll just mention it one more time. So this Tuesday is our very first demo day of the semester. I was trying to come up with some really clever ways that we would participate and share our designs. But I think what I'll just do is just create a Google slide deck and invite everyone to edit it and just insert just a few slides per each team. And we should be able to get through the MP0 demos for each team in plenty of time. Even 10 minutes would probably be too much for you to talk about your own MP0 design. So I'll put together a quick little template of what I'd like you to talk about on that demo day. Yeah, feel free to be creative and talk about other things and add your own personal touch on how you'd like to do that presentation as a team. It's not meant to be a stressful type of presentation. I think you'll find that in this class, while everyone's been kind of in their own little private channels and working on things, I think you'll find that your peers really do want to learn more about what you were able to do, what things worked well, what challenges you faced along the way. Maybe by the time we get to the sixth or seventh presentation, there'll be some repetition, but I think you'll find that um, maybe unlike a presentation for a senior design course where everyone's working on completely different things, because you're all sort of individually trying to work towards a common goal. You'll see a lot of interest amongst your peers here and a lot of good Q&A, not from me, but from the other students in the class. So I think we'll do it that way. And then, I don't know if I'll be able to record the audio properly, and we'll give that a try for Tuesday, and then we'll continue to experiment with that format as the semester continues. Um, and so you keep that in mind. So a lot of teams are now very close to done with MP0, and that's wonderful. It's due Monday, so get that done and submitted Monday at any time of day. Um, and then just take a little bit of time and put together a couple slides for Tuesday morning. And then the thing I will mention on Tuesday, but just before I forget, I want to mention it now, is that all of these labs are going to be having that pre-lab aspect as well. And the MP0 pre-lab wasn't anything. It was just sign this paperwork, and so I didn't care if you got that done beforehand. You wouldn't have known to get it done beforehand. MP1 and going forward have a legitimate pre-lab, and it's a little bit of a time crunch. You'll be finishing up MP0 and kind of maybe done with the lab for a little while, not wanting to think about it for a couple of days. But just take time as a team, and again, you can split that up amongst the team members however you see fit. I think it's important that everybody know some aspects of the pre-lab, but you don't have to individually work on it. And I would just like everybody to uh, get that done before the start of that lab on Wednesday, and just upload that in the first couple of minutes in lab on Wednesday. They're not meant to be busy work. You could think of them as homework assignments, but they're not. They're really just getting you started the right way on that next lab assignment. Otherwise, my concern would be that first few hours of that first week of lab we have together for a given assignment would only be spent on basically doing the same kind of things the pre-lab is asking you to do anyway. So they're meant to accelerate your progress, and they're meant to catch any misconceptions, early on versus 7 days into the assignment. So that'll be our schedule. Monday at some point, you can do it earlier if you want. Hit submit in Canvas, get MP0 done. At some point, update slides for our Tuesday demo day and have a couple of your team members present. It seems like basically everyone's showing up. So come to class on that Tuesday and present when it's your time. And then before Wednesday morning, then submit the pre-lab for the next assignment. That'll be our somewhat busy weeks where we have all those things kind of due back to back to back. The pre-labs are meant to be doable in a reasonable short period of time. So just get together as a team, have a maybe debriefing of the previous assignment, and then look together at the next assignment. And then the thought is once our lab actually starts on Wednesday, you'll really be able to hit the ground running and make a lot of progress when we start. So with all that aside, where we left off on Tuesday, we're starting to get into some of the just lower level details of what it means to display an image. But before we can really worry about what it means to render an image, what does it mean to actually do that final physical display? And we just left off talking about, you have this region of memory, this frame buffer that is storing the information needed to know what a pixel should look like on your screen. And a very common secondary consideration for having frame buffer based displays is the concern that you're using that region of memory for two things simultaneously. You're both writing to it, whatever rendering algorithm you're implementing, either in hardware or in software. You're writing to that region of memory, and then you're also simultaneously reading from it. We talked briefly on Tuesday about there's some sort of analog digital analog conversion going on, some sort of DMA or other circuitry that's reading from that memory region and using it to drive a controller to determine what the actual pixel values should look like and what those colors correspond to. So both those things are happening simultaneously. You can think of it as one software process is writing to a memory region, another software process is reading from that memory region, or it's hardware, it doesn't matter. But two things are happening simultaneously. And like in all kind of synchronization concerns, when you have those two things happening simultaneously, there can be an issue of synchronizing that operation. And so we typically employ double buffering. It's not a requirement, but we typically employ double buffering in graphic systems, at least double buffering. You'll see triple buffering and other things as well, where we have one region of memory that's dedicated to the writing procedure and a separate region of memory that's dedicated to the reading procedure, so that we're never actually writing to the same region of memory that we're reading from at any given time. It's not a bandwidth optimization. You're still using, 2x the bandwidth to do both a write and a read simultaneously. It just allows for the display to look a lot more less choppy. Because otherwise, what could happen if you think about it? You're writing to your frame buffer region, you're seeing or you're updating those values in memory, those gray regions in memory corresponding to what your next pixel is going to actually over here. Those ones and zeros in memory corresponding to what will be your gray pixel in the screen here. And while you're doing that writing, you're also separately doing that reading. If it's from the same exact region of memory, then you're actually going to potentially be able to see that redraw happening as it's happening. And maybe you'll see half of the previous frame while you're looking at the current frame. That is a common problem that we always have to deal with in computer graphics. The simplest solution from the rendering system's perspective is just to have two buffers, one that we write into, one that we read from, and then when it comes time to actually do the display and we're done doing the display, we can just swap the two buffers. One physical memory, you can think of it as just keeping track of two pointers into our memory. What's my current active write buffer? What's my current active read buffer? When I'm done with all my writing operations, I can then do a swapping of those frame buffers and just switch the two pointers around so that whenever we're drawing to display, that region of memory is fixed during that draw call. That's what double buffering refers to. We talked a little bit about the memory technology involved here. We learned a little bit about this memory technology in your CPRE 381 course. Those of you who took that, um, there's similar considerations, right? Our challenge is getting enough bandwidth in this case for our frame buffers, but in general for any of our computing needs, we have an equivalent bandwidth needs, and the technologies have co-evolved over time. There was a period of time in which our memory was able to keep pace on effectively a cycle per cycle basis with our computing fabric, and that hasn't been the case and will not be the case again anytime soon. Um, so when we have different memory technologies, we have to consider, well, what is our actual bandwidth requirements? At least for a graphics processing system, it's a lot easier to do that math. I mean, the argument can be made, more is just better. So just give us more bandwidth and we'll find ways to make use of it. But at least just for the task of reading and writing a frame to be displayed on a screen, we can do that back of the envelope calculation, like we actually did last week, pretty quickly. Given a specified resolution, in this case 1280 by 1024, also given a amount of bits per pixel, we'll talk about more about that in a little bit here, and then given the refresh rate, how many times we actually want to read from that buffer in memory, presumably also how many times we would potentially want to write to that buffer in memory, we can do the back of the envelope calculation of what is our gigabits per second required out of that memory technology. More is better. And as we do talk about when you take 381, that ideally we can make use of SRAM, where it's much faster, the fundamental technology than DRAM is, but it's also much less dense. We can fit much less of it on chip at a given time. So while your SRAM sizes tend to be measured in kilobytes to small low-digit megabytes, you can certainly get your DRAM into the gigabyte range relatively easily nowadays. Um, Physically, the actual underlying semiconductor technology doesn't necessarily concern us other than the fact that we have to be aware there's latency associated with these operations. Logically, it's laid out as a two-dimensional array where you have your columns, and then in each column you have a certain number of rows corresponding then to each individual memory bit here. So we go back and forth with that visualization, right? When thinking about a frame buffer, it's nice to visualize it as a two-dimensional data type, right? Frame with our screen has a certain horizontal and vertical resolution. That's a nice way to visualize it. And then I always keep mentioning, well, yes, it's two-dimensional, but ultimately you have addresses in memory that are sequential. So there's a little bit of that array math that you have to do at some point along the way of given an XY location on screen, that corresponds to we could do the math. X times vertical resolution plus Y actual linear address in our memory. But now I'm telling you that actually, in reality, that does then correspond ultimately to some row and column layout in memory. But this row and column layout of our DRAM doesn't correspond at all to our resolution of our screen. This is a physical layout of the memory on the chip. And we don't generally have to know what that two-dimensional layout is on our chip. Um, and you can think of it also of having a third dimension. If this is describing a single bank of our DRAM memory, our DIMMs, our devices we actually purchase and put in our workstations, would have multiple of those individual logic banks there. So it's almost a three-dimensional layout in that sense. There's a quick question, what is SRAM um, actually used for? Well, certainly for cache. So when we want a small amount of relatively high speed storage. That's the trade off we're making when we choose SRAM over DRAM. That's where things like that's we want to use a cache. By having a relatively small amount of that really fast, not so dense, so it takes up a lot of space, memory on our chip, we can maybe get some of the benefits of that high speed without having to pay the huge budget of having a gigabyte somehow of our SRAM technology. This is also, we will take advantage of that as well. Um, 381, we spent like 3 weeks talking about locality until everyone's really sick of looking at locality in our examples. But locality is very relevant for graphics processing as well. We're accessing these frames of memory for our result of our graphics processing operations. There's going to be a ton of locality there for that reason. Um, if I'm going to render, pixel at XY location, it's extremely likely I am next going to want to render X plus one comma Y next, the next one that would correspond to the next address in memory. You just get a ton of spatial locality. So in modern graphics processors, what you'll see is even having what we would consider a relatively Spartan amount of SRAM cache on the device, that number is creeping upwards, but it's still a relatively small amount. You can still get extremely good cache performance out of it because there's just a very regular, reliable memory access pattern. That's just a fundamental feature of doing graphics processing. Yeah, it's a good question, Matt. I mean, so I said SRAM cache is one reason or one way you would see SRAM in your design. That's a common way. A lot of processors, and for many, many years, this isn't not necessarily a new invention, would also have separate SRAM memory, small little software addressable memories for all sorts of purposes. And depending on the context of how it's used, it would have a different term associated with it. Scratchpad memory in the embedded system space, where we have a cache, but that's hardware managed. I, as the application developer in the embedded realm, know exactly what I want my access pattern to be. I then have a software managed cache. Modern GPUs let you do a little bit of that as well. There's shared memory between the individual cores in the GPU, and then those are software managed. It's not a cache controller taking care of it. It's you as the application developer determining what needs to go into that memory versus what can go off into our DRAM there. This is, but ultimately, this is not a transistor technology course. This is not a VLSI course. You could teach graphics processing from the VLSI perspective directly. Um, I think suffice we need to understand some of the fundamentals of why that DRAM exists. So the big picture there is it's there because we do need a large amount of memory. So that's why we can't just do SRAM for our graphics processing system. Just doing the basic math there, the issue is not necessarily the throughput consideration. It's just that total storage. 1280 by 1024 to store, um, in this case, a 4 byte buffer would be 4 megabytes. Well, it's actually a little bit more than that, but roughly 4 megabytes there, right? Uh, And that's just to store a single frame. Well, I just told you it's good to have double frame buffers, double buffering. That's now 8 megabytes. And we need all sorts of storage for all the other stuff that goes into our graphics rendering. That number is going to grow pretty quickly. That becomes pretty infeasible for SRAM. So SRAM could, in theory, be a nice technology for us, but that's why we have that DRAM here. The downside of the DRAM, beyond issues of latency and things like that, is the complexity associated with actually interfacing to it. So we in a previous iteration of this class, we actually spent a lot of time building a DRAM controller and understanding all the timing associated with DRAM. And this is a little bit of an artifact of those earlier days where you have ultimately what's going to be a somewhat complicated state machine where you're first figuring out that row access stage, that given an input address, figure out what the row address corresponds to, and start to pre-charge that particular row so that we can start to read values from it. Then there'd be a column access side where, depending on what the rest of the bits of the address are, decode that into the actual column or columns that we actually know. All while periodically, because of the fundamental nature of DRAM, charging those lines so that we don't actually lose information stored in that memory. Those DRAM controllers become pretty awful quickly. I just here's just a semblance of just a DDR one initial generation DRAM timing sheet, and a very small part of that. You could build a DRAM timing controller in this course. Given a data sheet, and that Micron data sheet, I can provide it for you if you're interested, is several hundred pages long. Because ultimately, the spec is all about very precise timings to be able to get certain benefits of throughput off the device. We could do that. It would take us a good chunk of our time. That would be a good chunk of this semester building that DRAM controller. But we do need a DRAM controller in our system. It does turn out in practice, there's more than one company whose entire reason for existing is to provide memory controller intellectual property. So you have a company like Micron who provides the actual physical DRAM, as well as enough information to implement a memory controller for the modules that they themselves have. And then there's other companies whose entire intellectual property is creating cores, providing licenses for cores to allow you to instantiate a DRAM controller in the rest of your design. This semester, we'll use Xilinx's IP for that purpose, which works just well enough on the DRAM on some of the boards that they provide for you to use as well, including the one that we use. And when we look at those different specs for DRAM, the main difference, there's nothing magical that happens as we go from DDR to DDR2 to DDR3 to DDR4. There is generally a specification committee that gets together that agrees upon certain things, certain tolerances, and it's just incremental improvement in the timing and the signaling requirements for that interface. To have this particular pre-charge line, it needs to have a value that goes high for 11.2 nanoseconds, um, and then stays down for 30.6 nanoseconds. And then likewise, this signal, this wire has to be of exactly this impedance in order for this sense amplifier to work properly. All of those very low level VLSI kind of tolerances and specifications are what go into something like a DDR or DDR2 or so forth spec. There's nothing magical about it. There's an understanding of what current fabrication technology is capable of doing, and also attempting to be a little bit forward looking in terms of we set the spec to be a little bit aggressive so that perhaps 5 years from now we can actually manufacture what is the higher end of what that specification provides. And then the various companies whose have that role in that supply chain determine how to create the IP, how to physically manufacture the chips that would adhere to that given spec. So it's a little bit of a chicken and egg thing, that there's an understanding of what is possible both now and for some foreseeable future time horizon. And then the specification comes from that. What we think we can do now, what we would like to be able to do in the relatively near term future. And let's set a spec that allows us to build systems ultimately that can achieve that. So when you see something like, here's the DDR 400 spec that has a certain specified transfer rate, that's just a function of, how many lines of control would be allowed, or how many data lines would be allowed in a given implementation, and ultimately what clock rates they're spec to run at. Same for the remainder of these as well. When you look at the difference between DDR2 and DDR3, fundamental difference is both the number of data lines and the clock frequency that those lines could be accessed at. And so when we look at something like, GDDR6, so what's currently still in the highest of high-end GPUs there, big takeaways, there's really nothing magical about it. In terms of the data sheet for it, in terms of the actual state machine for how we would interface with it, it would still look very similar to this. The main difference would be just tighter windows in terms of what is allowable, in terms of the clock frequencies, in terms of the characteristics of the signals traveling on those lines. And then there's an agreed upon spec that says, okay, we're going to call this version 6 of our graphics appropriate RAM. It has a couple of slightly different trade-offs between latency and throughput versus conventional DDR memory, but otherwise they are extremely similar. But we've evolved to this point over time that now if you do have GDDR6 memory in your system, there's both a theory and a practice of it, but at least in theory, given a certain number of lanes, which that number has also grown quite large, there's a lot of wires coming off this device. You're reaching really unheard of throughput in terms of how much memory bandwidth you can get back out. So we started with thinking about our 1280 by 1024 frame buffer, and we would need 360 megabytes per second to be able to access it. And the reality is today, of course, we can do that, right? We've been able to do that for years and years and years. But now we have an incredible amount of theoretical bandwidth that we can take advantage of in our system. And that really enables us to think about graphics processing a little different than we had before. Latency is still quite high when accessing our DRAM. The controller we build for it is still really messy and ugly, but hopefully we purchase that or we use that. We don't build that ourselves if we're worried more about the architecture of the rest of the system. But then what we get back out is a real high throughput machine, right? What we can really get would be our 600, 700, 800 gigabytes per second of throughput. That enables a lot of things that even a few years ago would have been thought of as impossible. In terms of what you have this semester, it'd be nice if I had an FPGA board for you. Um, if I had an FPGA board for you that had GDDR6, I don't. Uh, there's a big price differential as you go from DDR2 to DDR3. So what we have is DDR2 800 that has a maximum transfer rate of 6.4 gigabytes per second, which sounds good enough, right? Based on what I just said about the resolutions we would typically want to support and the amount of bytes we would have to store in our frame buffer and wanting to read and write from those bytes in the frame buffer potentially multiple times per frame, the math still kind of works out, right? 6.4 gigabytes is a lot bigger than what was that? What was the number we had before? The 360 megabytes, right? That gives us a couple orders of magnitude of wiggle room to work things out. One of my favorite Yogi Berra quotes is has to do with something like this, right? The difference between theory and practice. I'm going to completely mangle the quote from him. It's in theory there's no difference between theory and practice, but in practice there is, right? That you have a spec sheet, you have something that's rated at being able to handle 6.4 gigabytes per second, maximizing that bandwidth, actually getting anywhere near close to approximating that number is the or a fundamental challenge in the design of computing systems. You may have a DDR module connected to the rest of your system that has a maximum specified throughput. Actually getting that number back out is a very hard thing to do, both in terms of designing the rest of the architecture around it, and as well as for any software running on the system as well, actually getting anywhere near that maximum amount uh, proves to be a very difficult thing. So a word of warning is that when you read a data sheet for something like a DDR that says, yes, for your board, and they certainly market it as such, it says, you have DDR2 800 RAM on this chip, on this device, on this board, and you can get 6.4 gigabytes per second out of it. In my experience, that's not at all true. The actual number is at least half that, or at least less than half that, and maybe even one fourth of that number. So we're starting to get a little closer in terms of maximizing and saturating our bandwidth on this particular device that we're using this semester. That's okay. That's a fun system design challenge to have. We only have so much, and we have a certain need that we have. How do we make sure that we don't oversaturate our bandwidth and that we don't drop our frame rate accordingly? Yeah, so when we talk about lanes of data in the DDR spec, and you could definitely take a look at it. Basically, each of them allows us for an independent transfer of a single bit of data. So the actual math of what our theoretical throughput is or bandwidth transfer rate out of a DDR system. It's clock rate, and then it's both positive and it's differential. So both on the rising and falling edge of that clock, you can transfer a bit of data, and then you have a certain number of lanes, and so you're basically just multiplying for the given clock rate, maximum clock rate, that number times two times 384 to get that total number back out. Not a dumb question at all about graphics DRAM, simply referred to as VRAM. Um, VRAM is kind of a there's nothing wrong with the term. It's kind of a dated term. Um, it really depends on the system whether you ultimately have something referred to as video RAM, or if that's just a logical way of viewing a certain region of memory in your system. Um, so when we talk about frame buffer devices in Linux, like when you first boot up your Linux system and it doesn't even know it has a graphics processor attached yet, and it wants to show something in the BIOS, it's just going to have some region of memory that it's going to dedicate to putting that frame information in to display that very basic information to start up. So it would be a logical way of looking at you could think of this as the video region of memory where we want to display our output. DDR then would be the underlying implementation technology of it that allows us to get really high resolution graphics back out and keep that memory updated as many times per second as we need it to be. Actually, testing bandwidth is a little tricky. This is my very high level diagram of the different types of memory interconnects you have in a typical modern day GPU based system. As I've mentioned before, we always have that CPU in the system somewhere. And nowadays, with systems, you do get effectively a unified address space. It's not truly a unified address space, but from the virtual memory's perspective, you have certain pointers that are going to correspond to data that is resident in the CPU's DRAM, and you're going to have certain parts of your address space that's going to correspond to data that's actually physically resident on your device. That's the CUDA term, but your GPU memory. And by having one unified address space, that does make the programmer's view of the system much simpler. You don't have to worry as much about how do I allocate data, when do I have to explicitly copy things back from one device to the other, from the CPU to the GPU, or vice versa. But the reality is still there that there's going to be certain copies that are going to be relatively fast because they're going to be host to host copies. I have a region in my CPU's DRAM, maybe cache is holding it for me, and I need to copy it. That's going to be relatively fast. That's going to be your DDR5 memory in that system. And then you have the GPU that's also going to have device to device memory copies as well. Something is stored in my GDDR5 memory, and I want to do a copy to a copy. That should be relatively fast. But then you're also going to have those copies that are going to go in either direction, from the CPU to the GPU or the GPU to the CPU. If you have a virtualized memory address space, there's underlying, I hate to call it hardware magic, but there's underlying hardware memory transfer engines that take care of doing that for you. But the cost is still there. GDR has its own throughput that would be associated with these internal copies, those little feedback arrows here, those device to device copies from within the CPU or on the GPU side over here. That is our DDR bandwidth. Now when we have this arrow here, this is the bandwidth physically between devices. And now you're not looking at DDR bandwidth anymore. You're looking at things like PCI Express bandwidth, which is pretty good still, but because of the fundamental, signaling requirements of that type of interface, uh, where I have to be able to plug in a card, and actually I need to be able to run a certain length of cable to be able to have that connection there, it's always going to be significantly less than what your DDR to DDR type transfers can possibly have. Yep, possibly. So when we do those DMA actions, usually at least there's some sort of internal storage of the DMA engine itself, uh, at the very least to buffer enough so that it can do large block transfers at a given time. But you can, in fact, just request a single byte, and you're going to pay all the penalty of having that single byte of copy and get really none of the benefit of the potential throughput of such a high performance system there. My point here is also, I think, relevant that even benchmarking how much throughput you actually have is actually not that straightforward. Um, I'm opening up here. This is again back in the CUDA SDK. One thing I noted as I was walking through this code the other day is I think there's something fundamentally broken in the C programming language, that to write a program that just measures how much bandwidth you have between the GPU and the CPU and GPU to GPU transfers, there's just so much stuff that's required here. Uh, let's assume these are relatively high paid engineers who put this code together. Just checking the command line arguments for the various different options is something like 500 lines of code. So you open up these SDK applications, and you have to kind of hunt and find the actual interesting parts, which is a relatively small amount of the overall code base here. So it's checking command line flags, and then it's finally going to try to actually test the bandwidth. And when we look at what the CUDA call for testing the actual bandwidth here, see if I find the actual function that's doing anything interesting here. Um, Test device to host transfer. So device and host are CUDA specific terms. Host is the CPU, device is a GPU in the system. They could have called it test, GPU to CPU transfer. Um, we're not really into the CUDA side of things yet. Um, but some of this should look somewhat reasonable to you from just a C programming perspective. We're going to allocate a large block of memory, right? If you want to test your theoretical throughput, you don't want to copy one byte over. You want to copy a large amount of bytes over. So we're going to copy a big chunk of data over. We're going to initialize it to something. And then here's where we start to do some of the CUDA calls here. And we're actually going to allocate now memory on the device. The call looks very similar as it should be. That's CUDA-malloc. So you'll find that for almost everything you want to do on your host computer with regards to managing resources in memory, there's an equivalent call that does it on the GPU. That is just prefixed with CUDA. So we have a malloc call up there. We now have a CUDA-malloc call here. And basically the only thing we're doing is a memcopy. So you familiar with a memcopy call that copies from one region to another region on a CPU? CUDA memcopy. We're specifying our two pointers, the amount of bytes we want to copy, and then a certain flag that actually tells us the direction that we're doing that copy. It's not that obvious in the CUDA context what direction we want to otherwise do the copy. Yeah, they could have used Boost, but even the Boost version of this code that does first off, that's a big nasty dependency you now have, but even the Boost version of this code would look pretty ugly. That's just a limitation in C++ programming, I think. So that's all this bandwidth test is doing. So allocate a big region of memory, initialize it with something that doesn't get optimized away by the compiler, copy it, do a memcopy call, and then use a timer function to actually check did it actually how long did it actually take, and then ultimately there should be some coding here that does a little bit of math. We've done the copy, convert that to gigabytes per second. So take the amount of data, divide by a billion to get gigabytes per second. We can run it quickly. It's not an exciting looking code. Um, this would be a system. This is the Maxwell system again with GDDR5 memory. So in theory, we should be able to get a ton of bandwidth back out. Um, but we're actually limited in practice, even for an application that's doing nothing other than just copying big blocks of memory. It's not doing any work whatsoever on that memory. There's nothing delaying those transfers from happening. Um, Internal to the device, we're doing pretty good, right? That's 245 gigabytes per second. Looking at the code, let's go back to our GDR listing here. Looking back at the code, um, it doesn't seem to be doing anything to hide the fact that there's a cache present, which is fine, but then that's not really DDR bandwidth that it's checking. It's system bandwidth, which is also important and relevant to us, but the cache is probably helping in that bandwidth calculation that's happening there. Um, we're getting a number that's pretty reasonable given GDDR5 memory. But in reality, we're going to be wanting to pass a lot of data from the CPU to the GPU and vice versa. Our code, our OpenGL code and our CUDA code is running on the CPU. It is in charge ultimately of making sure that you're interfacing with the operating system properly, of um, of allocating resources, doing all the things that we expect our CPU based code to have to do, collecting the results, actually opening up the window to display a visual result that we have back out, and just doing things that require interfacing with the operating system. That is slowly changing, but that is still fundamentally the domain of the CPU, still the host in this system. When we look at that bandwidth, CPU to GPU, what they're calling host to device and device to host bandwidth, um, now we see a much lower number: 12.4, 12.5 gigabytes per second. So we talked a little bit on Tuesday about bottlenecks in the system and how they can be at various different places. This is the first place. This is the first place that bottleneck is going to occur. If I want to stream data from my CPU into my GPU, or if I just want to have a virtualized address space where it's unified and it's shared, and I can just write C code that doesn't even know what things are on the GPU and vice versa, that's going to be our fundamental bandwidth number, and that's a lot less than what the DDR chips on the individual devices would be capable of. So we think about those bottlenecks in a rendering system, and that's the first one here. And while I'm not going to walk you through all the evolution of OpenGL over time, there's a lot to talk about there. But from early days of OpenGL to modern days of OpenGL, and also to look at what some of the other modern APIs are doing, what Vulkan is attempting to do, what Metal API is attempting to do, it seems to me that a fundamental design criteria of all of those newer versions of APIs, including OpenGL 4, is to try to work around this problem. To try to minimize the amount of times I have to send data from the CPU to the GPU so that I can be doing all my graphics processing with this much bandwidth versus having to rely on almost any other step along the way in that bandwidth that we have. So remember that when we start to talk about the API, when you see function calls that look just kind of awful in OpenGL, there was a time I considered having this to be a Vulkan class, but we would have to write so many wrappers it would have looked like OpenGL anyway for us. Um, a lot of that is to provide more power to the GPU itself, so that we can send some initial get going data from the CPU to the GPU for a given frame, and then that GPU can operate in as independent of a fashion as possible and report back, I'm done. The frame is over. Give me the next frame. Give me the next starting information for the next frame, so that as much of the processing could be done this way versus having to deal with that bandwidth number that we have there. I have a couple slides here about different display technologies. There is a point here that is beyond just knowing that different displays work differently. CRTs are one of the earliest display technologies, and the design of CRT displays still fundamentally influences how we do display technologies today. So CRT, cathode ray tube. So you have an actual physical device here that is controlled, and it's modulating an electron gun that boils off the electron and fires them at a display. And that display, that actual kind of curved monitor glass you have in the front, is actually coated with a phosphorescent substance that allows it to light up when electrons hit it. And there's red phosphors, green phosphors, and blue phosphors. And by modulating that electron gun, it's basically firing things at the screen at a certain precision, you can get things to light up in different colors. And so a lot of what's happening in that circuitry is control logic that takes in the input signals, and we'll talk about the actual VGA signals that are coming in here. And as this thing is scanning its way through the system, and it's physically that raster scan we were talking about is actual physical process happening in this style of display. We have control circuitry that's modulating how bright, how many electrons are we firing off for the red, blue, and green of every individual equivalent of a pixel location that we have there. To do that properly requires a really high voltage display, which is why people say don't open up old CRT monitors unless you're sure you've discharged those capacitors properly, because they're fun and they're potentially lethal. There's all sorts of other displays where the fundamental difference is actually not in this part. This part is still pretty much how we do things, with some slightly different signaling requirements and some slightly different ways of encoding the information. This basically is still how we do display technologies, even with the most modern display technologies. The actual that's how we do display interfacing, even with most modern display technologies. Right now, I have a USB C cable connected to a docking station connected to a display port. Still really similar to a VGA cable. It's just got tighter constraints and tighter timing associated with it. The actual display, the physical display technologies have changed and are continuing to evolve. But ultimately, you can still think of them all, whether they be LCDs or plasma displays or all sorts of the LED variants that are out there, as still being a controller that for a given location that it wants to light up on the screen, controlling separately the R, G, and B components of that display. LCDs have a semiconductor component that allows light to either polarize and pass through or not pass through for the individual R, G, and B locations that it wants to display. So here's light passing through, here's light not passing through based on that liquid crystal that is being individually gated or opened up there. Plasma displays are a very similar concept, except we have uh, crossing compares of conductors that allow it to glowing plasma to actually pass through or not pass through things here. And for any sort of structure like OLEDs and things of that nature, it's a very similar concept. Different than the CRT, which is really just lighting up phosphors on a display based on the amount of electrons we're passing it. Basically, a semiconductor gate that allows light to pass through individually for red, green, and blue filters for a given pixel. So that fundamental color theory we'll talk a little bit more today has not really changed. And our view of the frame buffer ultimately then has not really changed. With what's changed is the amount of bits we have stored, what changes our bandwidth needs of grabbing those values from a frame buffer. But ultimately, whether you have an old school CRT running at 640 by 480 or you have a 4K LED display, something extremely similar is ultimately happening in terms of based on a value stored in the frame buffer, I want to let a certain amount of light pass through or not pass through for that location for R, G, and B for that location in our frame buffer. And that VGA controller concept, even though the term itself admittedly sounds kind of dated, right? Engineers tend to collect boxes of random cables, and I finally threw out all my old all my old VGA cables because I was finally out of devices that actually needed them. But the actual controller, the display technology for it, the interfacing technology for it, is still very much how we do things. Um, so as VGA, not as the actual cable, but as a controller standard, is still fundamental how we display images on a screen. This view of the raster display we talked about on Tuesday, where we have the horizontal drawing period followed by a brief horizontal retrace period. To back in the day, to physically let the electron gun move back to the beginning of the line. It's nothing as physical happening now, but that blinking period associated with it, and going row by row by row in that raster pattern, and then eventually making its way back to the beginning where we have a vertical retrace and for vertical retrace period. That timing information, and there's aspects of it. So that timing information is still part of our VGA standard. It originally corresponded to what was physically happening in a CRT monitor, but we still take that timing information into account. So while modern displays that use VGA controller circuitry, they accommodate different resolutions, and the way it works is that that controller circuit is dictating the resolution by producing certain timing signals that control those raster patterns that we have there. So there's certain synchronization pulses that happen here, where in between where we're displaying active video, there's a horizontal sync pulse of a certain specified amount of time that lets the display controller know here's how much time it's going to be until the next line is going to be drawn. And likewise, when the entire display is drawn, here's the amount of time before we can retrace and get back to the beginning of it. So this kind of display timing diagram here, which is shown for the horizontal phase, would have a very similar timing diagram for the vertical phase. And the size of these gaps, both the sync gap as well as the so-called front porch, the time between the start of the horizontal pulse and the actual active video, and the opposite end is called the back porch here. That is what ultimately is going to dictate what our resolution is of our display attached. Given a size of these pulses, there's standard specifications that say, here's how many pixels is going to be in that individual display, in that individual row here to be displayed for that horizontal active period. And so when we talk about the difference between a 640 by 480 uh, VGA cable connected to an old school CRT monitor, or even things even more basic that are composite video cables, um, versus a 4K display refreshing at 120 hertz, the main difference is the size of those pulses in this version of the same. So this version of the diagram is kind of showing both the horizontal timing and the vertical timing here, but it's still effectively modeling what was physically happening in those old CRT style displays. That there was physically amount of time needed to kind of get the thing to go back to the beginning of the next row, and likewise to retrace back to the beginning of the frame. So the main difference between 640 by 480 resolution from the display controller's perspective and 8K resolution, as I show here, is really just the times associated with that, and then the corresponding clock frequency you would need to be able to generate a unique value for every pixel in that amount of time you have dedicated to that active pixel time. So the logic is actually the same. I can build a VGA timing controller that can handle any resolution within a given spec. The main difference is then what clock it actually would need to have to be able to generate the signals at the right time. The link you can access offline, we can open it up briefly here, has a really cool timing calculator. It's not doing anything other than the math associated with the spec, so it's not that clever in that sense. But I think it's kind of cool that when you go there, you can just specify for my given resolution, what does that correspond to from a timing. If you work long enough with this, some of these things you start to memorize. That 640 by 480 is a 25 megahertz clock, even though this here says 23.75. Um, well, the truth is also that there's a certain clock specified for it, and you don't normally have to exactly hit that clock number there because there's enough tolerance built into the actual displays you're interfacing with that if say that it requires 23.75, which is not the right number, but it's close enough, um, and I give it a 25 megahertz clock, it'll work well enough, and you won't notice any glitchiness or anything like that. What I actually like about this timing calculator is not this, which is this is just a lookup table of this part here. For a given resolution spec, here is what the size of horizontal pixels are. Here's how many rows there are, or here's the size of each row. Here's the number of rows that we have here. Here's the size of those individual synchronization pulses to be able to generate a valid signal at that resolution. What I actually like about this timing calculator, and that's nice as well, is it actually tells you that given different display cabling technologies and what type of throughputs those cabling technologies allow for, whether or not you'll be able to handle transmitting that resolution over that particular display. One thing I was curious about when designing for this semester is that if we did have a 1080p 60 hertz display that we wanted to use for our simple graphics processor, and that's the upper limit of what we support successfully this semester. What would that mean from a physical interfacing perspective? Now, I know HDMI can handle that, right? Various HDMI specs that people tend to use, and you don't see 1.0 HDMI cables anywhere, can handle it just fine. If I wanted to instead use my gigabit Ethernet interface and just stream video over that, would I be able to do that for 1080p? I could do some of the math in my head, but this calculator is really useful to tell me. Well, actually, unfortunately, the answer is no. But you can get pretty close. So your 3x, you need 3x the bandwidth of what gigabit Ethernet provides for you. That means I can't do a 60 hertz signal, but I can do a 20 hertz signal. So there's a lot we're going to be able to stream into our design just using that gigabit Ethernet interface we have starting in MP1. The numbers get a little crazy once you start to crank up the resolution. I actually have a little trouble even imagining what that circuit for that display controller would look like for an 8K TV. If someone would like to donate one for the purposes of class experimentation, I would happily accept that donation. But for an 8K TV, um, we know that's a lot of pixels, but the resulting clocking requirements is pretty intense as well. So somebody out there has designed intellectual property that generates signals at that resolution and can actually manage and process signals at that clock frequency. So for roughly for your 8K display, you need an 8K clock to be able to handle that, and that's a pretty fast clock. Um, if this if this calculator is correct, and there must be something I'm misunderstanding with regards to it. According to that, nothing can drive an 8K display. So I know that's not the case, but maybe there's really limited interfacing form factors that allow you to actually correctly drive an 8K display, or there's some compression techniques that are happening, and you're not truly drawing a multiple 8K frames at that refresh rate with a single port. Um, Right, using multiple display ports, according to this calculation, it has to use 3 though. So I do wonder about that, or if there's ways it can do by compressing that stream to get that information to fit over the cable. So it's not true 8K, I guess, right? If you truly wanted to show uh, 8,000 by whatever it is, 3,000, whatever the horizontal resolution is, 8,000 by 4,000 different pixels with no compression whatsoever. You wouldn't be able to do that with a single DisplayPort cable there. But to me, just looking at those throughput requirements, it's a little mind-boggling. So um, for our purposes, we're going to stick in this what we used to call full HD, this 1080p 60 hertz frame of reference. That should be okay for our DDR2 memory on the board. And it should be okay, of course, for displaying this on the attached monitor. And then even when we want to display a lot of that information and copy it over our gigabit Ethernet, we're not there. Should be close enough to do reasonably decently over that gigabit Ethernet. But keeping in mind that all of those theoretical throughput requirements are best case scenarios, right? Um, Let me rephrase that just to be careful. The actual information we need to process to transmit is not theoretical. We need to send that much information, barring any compression, which is a good point, over that line, given that resolution specified. What our gigabit Ethernet can actually handle. Well, now we're back to that bandwidth testing scenario. There's something that's this specified rated limit of what this given network card can do. If it's gigabit Ethernet compliant, it should be able to, in theory, do this. In practice, can it get even half of that? Is something we'll have to find out as we explore with our simple graphics processing infrastructure. And finally, the last kind of little getting everyone on the same page topic here, just our mishmash topic here for lecture two, is talking about color models. We've talked a little bit about it already, but color is something that we do need to understand, specifically how light and color interact with each other, because that's fundamental to doing any kind of rendering. And here I'm not even talking about advanced rendering techniques that require tracing rays of light through a scene and determining what each individual pixel should be. If I want to draw anything other than just flat looking triangles, I need to understand how light and color interact with each other. And there's quite a different number of vernaculars one can use to talk about color, the tint, the shade, the hue, the brightness, and there's different color models that allow us to represent color using those different vernaculars and those different characteristics of color. But in general, we do need to know the basics of how light and color interact. We do need to actually know the answer to why the sky is blue to be able to understand graphics rendering. Now that's a good fourth grade question for everyone. Why is the sky blue? Well, we know the light is not blue, right? So the light is white. The light coming from the sun is roughly light, at least to the human eye. And it's actually, because it's white, it's actually a mixture of everything, right? So we have all the different colors of the rainbow when we have light coming in. Um, and in the process of getting from the sun to us, it gets refracted at various times. So the answer to this question, why is the sky blue? Well, the answer is it's not blue. It's not blue right now, right? The sky, if you look outside your window, there's a lot of clouds too, but the sky is some sort of grayish, whitish color. And it's a function of, as the light is passing through air, depending on what particles are in the air at any given time, causes the light to diffract in certain ways. And on nice, clear days, it's the blue wavelengths of light that tend to pass through. They oscillate a lot faster than the red parts of the light, right? And so you have the sky that's blue at that given time. But we certainly see red skies. Green skies aren't as common, but we do see colors of sky of all sorts of different colors of the rainbow. So why is sky blue? Well, it has to do with the interaction between the light that's coming in, the frequencies at which our eyes can perceive it, and various scattering effects that happen between the sun and our eyes. Two-page essay due on Thursday about why the sky is blue. Thank you. Um, and we do need to understand, how the human eye works at a very basic level to be able to do graphics rendering as well. Um, if you don't like thinking about how the human eye works, you can think of how a camera works, because we can also have that discussion as well. We need to have some semblance of that discussion as well, because as we'll see, as we're describing three-dimensional scenes, ultimately to be displayed on a two-dimensional monitor here for traditional graphics rendering, we're basically thinking about where do our eyes fit in when we look at a scene, when we look at the rest of the world around us. What is actually happening, and can we replicate that in our graphics rendering system? Or think of, if I point a camera at something, what is actually happening? It's a very similar concept. Cameras themselves are attempting to replicate some of what the human eye is doing as well. Um, but why can we see certain things? And apologize to color blind or other visually impaired students. But in general, what happens is, light comes in and we have a focusing lens at the front of our eye. And it allows us to focus that light to cells that are at the back, nervous system cells at the back of our eye, that allows us to collect information from that light as it's coming in. And you may have heard the term rods and cones in the back of our eye, right? Those are two different types of photoreceptor cells, right? Cells that can measure information from incoming light. And we have the rods on the periphery of our vision that determine, basic brightness. Is it light in the room or is it dark in the room? That's where your rods are most active. And then we have the cones, right, which are right in the smack dab in the center of our retina, and those are allowing us to determine basically what the red component, green component, and blue component is of the light coming in, because they're tuned to different wavelengths in our visual spectrum. So we have rods, and we have red cones, green cones, and blue cones, and there's quite a few people. I have a family member included who have issues with specifically our red and our green cones, and the connection between them and the rest of our nervous system that allows them to have trouble differentiating between certain combinations of color. And there are others who have problems entirely with their cones, and what they see are everything is just a shade of intensity. They're a more severe case there. But we have certain wavelengths of visible light, and then we have cells in our retina that allow us to perceive different aspects of that frequency at different intensities. And that signal, through the magic of our nervous system in our brain, gets collected together. And from light coming in, focused by our lenses, collected on our retinas, signal traveling to our brain tells us, I'm looking at something. Here is what the light is telling me that I'm looking. And if I completely turn off all the lights and close all the shades, and my light, those retinas are seeing nothing, right? And there's no light coming in, or effectively no light coming in, and what we see in that case is nothing. So because that there's a little bit of which came first, the understanding of the visual system, or the words used to describe whether something is red. That gets a little bit philosophical, but because of those fundamental physical processing happening in the human eye, and the corresponding physical processing that happens in camera-based systems, um, we can use that overlap in our retinal response to perceive effectively all the visible wavelengths to some degree or another. So the RGB color space is a way to attempt to represent what's happening there, where we have the three primary colors: our red channel, our green channel, and our blue channel, and we're adding them all up together in different intensities to produce other colors within that color space. There are many, many other color spaces that have been defined for various other purposes, and so the RGB color space actually has certain colors that it can't accurately represent, because it requires certain nonlinear mixtures of red, green, and blue to be able to represent. But the RGB color space is just adding up the intensities of those to generate combinations of those primary colors and all of the secondary colors that are corresponding to it. When I say it's perfect for display hardware, That's not an accident. So the display hardware is designed to also take advantage of that fact that we perceive red, green, and blue. If we have red, green, and blue lighting up phosphors on our CRT display, we will get pictures back out that are a reasonable approximation for what we would normally see when we are looking at the rest of the real world. So this isn't an accident that systems are designed to attempt to reflect what we see in reality, and the color space is following that design decision as well. But then going back to our frame buffer, as we are trying to store the information in our memory to correspond to those red, green, blue values, we actually have a lot of choices available. Good question about dithering. It's not quite what I'm talking about here because, well, we could get to that as well. So that is a good question. But let's talk about RGB color storage briefly. Um, Dithering generally refers to, if I believe, the printing process by which we can get color via combinations of things that aren't red, green, and blue. Red, green, blue is that additive process by which adding it to an otherwise completely dark display can allow us to add up to get us something white and many of the colors in between here. But in terms of storing the RGB information in our frame buffer, there's a lot of different choices. So you'll see things like 8-bit color or 8-bit storage per pixel, which isn't a lot of information, right? That's 8 bits to store all of the red, all of the green, and all of the blue. So typically, if you see something that has just 8 bits per pixel, there's some other piece of hardware in the loop there that is doing something with that information. Maybe it's applying the lookup table like we talked about on Tuesday. That 8-bit information actually isn't storing anything relating to red, green, and blue. It's storing an address into an intermediate buffer, a lookup table that actually maybe now has more bits per pixel associated with the red, green, and blue. 15-bit color mode is still extremely common, where you have 5 bits for red, green, and blue. Um, and 1 bit that can be used for other purposes, but is oftentimes actually just wasted in terms of storage in memory. That gives you 2 to the 15 different unique colors that can be generated, right? That's why it's 32K colors there. So 5 bits each for those channels. Each of those values, each of those 5-bit channels could have individually, separately, 32 different possible intensities. So we have 32 times 32 times 32, or just 2 to the 15 different colors that can be represented there. Another version that is extremely common is referred to as just 16-bit color, or you also hear it referred to as high color mode. And that's 5 bits for R and for blue, and then 6 bits for green. The thought being that in our modern computing systems, having things be multiple of bytes still makes a lot of sense for the hardware we design, for the software we write to be able to, for the architectures we have to process that information. So if we have 16 bits, we might as well make use of it. Um, why does green win out? It's a bit subtle. You really can't see it from this picture, but there's been more than enough, empirical analysis to be done to show that as humans in our retinal systems, we can actually differentiate a bit more green than we can red or blue. There's either, and I actually know, there's either more of those current cones for green, or they have a little bit more of a wider frequency response than the ones for blue and for red. So if one of the three colors gets a little bit more information, the one that makes sense is to have the green channel have effectively twice as many green colors that you can represent than the others. There's other types of so-called true color modes. Um, Generally, those refer to having 8 bits for the RGB information here. So that's 2 to the 24 colors that can be represented. That's a lot of different colors. Then what differentiates those true color modes is what do we do if we want to have an additional 8 bits there to have a 32-bit value. Just like it kind of makes sense to have some padding here, so we have these 16-bit values, and we don't have to do an awful amount of shifting and XORing to make sure we get the actual values we want back out. For our 8-bit color, this is also a common conundrum we have. We know that we want 8 bits for R, 8 bits for G, 8 bits for B. It's a very common example, a very common use case. Do we just keep everything as 24-bit values and then pack things into memory correspondingly? Or do we use that additional 8 bits just as a spacer to make our operations all 32-bit? Or do we try to implement something in those additional 8 bits? So actually, there's three possibilities there. That upper 8-bit either doesn't exist and we're just storing 24 bits at a time, or it's just blank, it's used for nothing at all, or it can be used to store other information such as an alpha channel for transparency information in an individual image. For our simple graphics processor design, uh, just had to make the call. We're doing 8-bit color, 32-bit pixels, of which the upper 8 bits is being used to store that alpha information. We don't use that for another 6 weeks of the semester, but we have that information there for when we want to do alpha blending later on in the semester. Um, and then nowadays, the sky is the really limit in terms of the amount of memory capacity we have. So there's all sorts of other things for advanced rendering techniques where you can have and do have potentially floating point buffers where the actual red, green, and blue isn't limited by integer depth and integer resolution. You can have floating point resolution for those individual channels. Ultimately, though, even if you're storing floating point information in your frame buffer, there's a piece of hardware that's going to have to do that conversion to an intensity that is something physical at the end of the day. And then you can have more than 8 bits of storage in modern systems as well. There's some interesting debate, both in terms of the frequency discussion of refresh rates as well as the color depth discussion of how much is good enough. Resolution, refresh rate, and color depth. How much is enough so that our displays are as good as we could ever want them to be? At some point, there's a limit, right? At some point, physically, the average or the reasonable human has a certain number of cones and rods and can perceive a certain amount and has a certain curvature of their lens and can perceive a certain amount of resolution and a certain amount of discrete colors. Consequently, how much is enough for that storage? We're getting pretty close to answering that question, I think, if we're not already there to get today. So that when I see, and maybe I'm just becoming kind of old fashioned here, when I see 8K resolution at 144 hertz, it makes me kind of wonder, uh, do I need it? Can I really tell the difference between a 4K display and an 8K display? Can I really tell the difference between 8 bits of red information versus 10 bits of red information? Well, I guess I don't really know that until I try it, but it's not that clear to me that we haven't already kind of reached the saturation point, no pun intended, of how much color and how much information we actually need to store for our frame buffer devices. If we're not there yet, we're extremely close to it. Our frame buffer needs are probably fixed. Our total memory needs are still going to continue to grow. So we're still okay in terms of needing more memory in our graphics systems. The algorithms we want to implement can take as much memory as we're willing to give them. There are many other color models. CMY is extremely common for printing, where by adding no color, you get white back out, and then to get black, you actually have to add full intensity of cyan, magenta, and yellow. Right, that makes sense for printing. Right, we're starting with white paper, and by default, much of what we want to print is going to be white. So having white be the default makes a lot of sense in that color space versus RGB, where you have to waste a lot of ink to get things to look white on that displayed page. CMYK is also extremely common as well, where K in some context refers to the key, in other context refers to the black channel of that color model. There's also very common in certain display technologies, luminance and chroma models. If you refer to YCB CR information being transmitted, um, that's what that's referring to. It's to me, it's not that interesting because the conversion from RGB to YCBCR is a very straightforward thing. It's just a very small amount of math provided there. But certain display interfaces work off that assumption that it can do separate types of compression on the input signal because the chroma information doesn't change. I don't recall which one gets compressed. I think it's the chroma information isn't needed to change that frequently, so you can compress it very naturally. Um, so that conversion can be worthwhile to transmit that information back out. And then there's quite a few others as well. HSL or HSV color models are useful for doing certain types of computer vision applications. It's easier to detect things in an image just based on the algorithms we have if it's in HSV format versus being in RGB format. Um, RGB still works for our purposes. That conversion may ultimately be happening on the cable going to the attached monitors you have for your Xilinx boxes, but all of our processing is going to then stay still in that RGB domain there. And I kind of like this Wikipedia picture showing how the different color models look, what it means to have RGB, the red component, the green component, the blue component added together gets you your entire picture versus your CMY. where it's just cyan, magenta, and yellow look different than RGB. Versus the CMYK, where you start with the black or the key channel, and then you add those components there, and then what some of the different color channels look like as well. What your luminance and chrominance models look like, quite a bit different than your RGB style models at the end of the day. And finally, I think it's interesting to know that a lot of computer graphics can be thought of as playing tricks on our eyes, coming up with approaches historically and over time and continuing to evolve today that allow us to generate an image that's good enough. And that trade off is something we'll keep coming back to as we discuss the various algorithms involved. That there's a certain reality that we want to try to display, and that there's a display technology that we're ultimately interfacing with. And that light is ultimately passing to the retinas at the back of our eyes, and our brains are taking the rest of the way there, taking it the rest of the way from there. A lot of computer graphics rendering algorithms are approaches to do just best effort. If we apply this approach to the incoming scene, the resulting render will look good enough. Uh, because our human processing systems are also, not perfect things either, and they can be tricked. They can be tricked to see things that aren't there. And so I thought just at the end of today's topic, I'd bring up a couple examples, more as a fun thing than anything else. But the big picture takeaway is our brains can get tricked pretty easily there. So curious, who thinks which side is darker in this slide that we have here, the left side or the right side? I guess left and right is relative to you're looking at the slide here, and it's reversed on my screen. Well, just pick left or right. What do you think? Left or right? Oh, don't say same, Matt. That's very difficult. Okay, fine. Yes, our brains are really tuned to see relative color changes, right? So that if we actually provide a little blocker that's not showing a little bit of the gradient that's actually there on both sides, we can actually see that without that little gradient to show us and to trick our minds into thinking otherwise, those two sides are exactly the same. And that's not a trick I'm playing on you. That's a trick your brain is playing on you, I guess you could say. Um, so that's something to keep in mind. That as we apply light models to scenes, we can generally only see relative color and relative brightness. We are not really good at determining absolute color and absolute brightness. And there's all sorts of fun color perception tricks that you can play on yourself. Even if you consider yourself a skeptical person, how about this one? Matt, you're not allowed to answer. Don't take it personally. Is How much would you say are different are the colors of squares A and B? All of you children who've grown up on the internet have maybe seen this one before, but this is probably my favorite of all the different color perception things here. How about which is darker, the square for A or the square for B? We have one vote for A and 28 votes for do not know. That's fine. Okay, a couple votes for A. I mean, I guess I'm trying to trick you, but I'm not trying to trick you in that sense. We look at this and say, well, yeah, A is darker than B. There's an object, it's casting a shadow, and on this checkerboard pattern, A is clearly darker than B. Um, but if I were to tell you they were the same, you wouldn't believe me. You'd say, no, you're wrong. So I actually go through and I grabbed that subset of A and in PowerPoint animation, move it over to B. I'm not changing the color of it as it goes. That's just a chunk of A copied out, cropped out, and copied over to B. And our brains can just not perceive absolute color and intensity. Sorry, Steve. Very well at all. So I provide a link here to what I call as a good time waster. You probably don't need a good time waster this semester. So save that link for some offline. This is one of the examples from that website. There are thousands such examples that our brains it does look like it's changing. It is not. That is literally me cropping it out and moving it physically over. I can show you the code for it in PowerPoint if you want to see it. Um, because of that, my goal is not to show you a bunch of brain twisters and perceptual tricks here. Um, it's distracting me. Because our brains can be tricked, because we have imprecise brains and our visual cortex isn't this perfect model of the universe, when we generate our graphics algorithms, that approach of saying what is good enough, what is something that when lit in a scene or when rendered as a line or as a triangle is going to look good enough to our brains. That is the compromise that we almost always make. Now maybe that those compromises change over time because the limitations of our hardware change over time. What our hardware is capable of changes over time. But that fundamental thought of we're generating an algorithm, we're building hardware, and it's going to do good enough so that our brains think it looks good enough is kind of the fundamental constraint of building our graphics rendering systems. So on Tuesday, we're going to have a demo day, and then we're going to continue on this topic on Thursday. I look forward to seeing lots of progress between now and Monday when MP0 is due. And I look forward to sharing the result of some teams and what scores they were able to get for MP0 between now and then. And I'm just really looking forward to our demo day as well. So, otherwise, enjoy, and I will see you on Tuesday.